All right, our next presenter is Adam Sealfon from Massachusetts Institute of Technology. His field is computer science, and his advisor is Shafi Goldwasser. And he performed his practicum at Lawrence Berkeley National Laboratory in 2015. Today, he'll be presenting on population stability, regulating size in the presence of an adversary.
Thanks very much. So since there are a lot of people here from very different backgrounds, before I get to population stability, I want to first take a step back and talk about some of the different problems that I've gotten interested in over the course of my grad school journey. So that stick figure is you, and pushing the boulder up the hill is the computational problem you want to solve. As we all know from Moore's law, computers have gotten a lot faster over the last few decades, so maybe the hill's gotten a bit shorter. So the sorts of problems that I find really interesting are when things don't go according to plan. So you want to solve your problem, but maybe your hardware isn't working. Maybe you're using some complicated computer system, and some pieces of it are unreliable. Maybe things go very wrong. Or maybe there's actually someone who's working against you and trying actively to prevent you from achieving your goals. So even though computers are a lot faster than they used to be, if there's someone working against you, that hurts you as well as it helps you, because your opponent's computer is also going to be faster. So this is perhaps the real title of my talk, Computing When Things Go Wrong. And over the course of grad school, I guess I've worked on problems of this flavor in 3 different areas: cryptography, privacy, and distributed algorithms. So I guess I'm going to start by saying a few words about each of these areas. So cryptography, the traditional question in cryptography, up through about the 1980s, is about private communication. How can I send a message to you so that you can read it, but no one else who might intercept the message can read it? And that we understand how to do pretty well. But sort of over the past couple of decades, there's been an increase in study about some other interesting questions that don't relate so much to private communication, but private computation. And the problem here is, suppose each of us has our own data, our own inputs, and we want to compute some function of our combined inputs, but we don't want to reveal our inputs to one another, so we only want to get the final output. So we want to compute in some way on data that's encrypted and just obtain the output. So for example, I might want to use some massively parallel cluster to perform my computation. But if it's not a DOE cluster, maybe it's owned by some company I don't trust, I want to be able to transform my data into some garbled form so that I can send it to this untrusted computer that can perform the computation for me, receive some answer that's still gibberish to that computer, but then when they send it back to me, I can decrypt the answer and learn the result of my computation. So I want to make someone else do the work for me, but I don't want to tell them what they're doing. Only I should learn the answer. So that's how this sort of problem comes up in cryptography. Another interesting area is data privacy, where the question is, our data may come from a variety of sources. So a lot of data sources, such as medical records, are things we don't want to publish, on the internet. But we want to make it available for analysis. We want to run analyses of the data and publish the results. And it's important when we publish the results that the original data of say the medical data of our test subjects isn't compromised. So this raises really important questions about what data, about what sorts of analyses are safe to release without leaking sensitive information. So there's this problem has a long history of ad hoc solutions that fail miserably. Sort of the traditional approach is removal of personally identifiable information. And the main problem with that approach is, depending on what other databases you have access to, pretty much everything is personally identifiable, including the things you want to study. So you can't just remove it. But over the last decade or so, there's been work in a field called differential privacy to obtain a principled and rigorous way so that provably you can draw conclusions from the data without revealing much about individual data records. So the third area I want to talk about is distributed algorithms, which is essentially the question of how can many individual processors coordinate to solve a problem, where the individual processors themselves may be very constrained and limited in terms of things like their computational power or memory, how much access they have to the input, and how they can communicate with each other, and so forth. And the individual processors themselves may be unreliable. They may crash, they may behave in arbitrary, and some of them may behave in arbitrary, unpredictable ways. And we still want to be able to compute. So this is close. This as a field is closely related to the parallel algorithms that we all know and love. The main difference is that in parallel algorithms, you tend to assume central coordination, whereas here you're assuming that the various processors are trying to compute something without the benefit of a central authority that's managing everything and coordinating everything. So each of these three areas has something in common in terms of how we model it, in terms of how things can go wrong. And we can model this in terms of an abstraction that we call an adversary. And an adversary, essentially, we can model the property we want as an interaction with the adversary. We call it a security game or a security experiment, where we have certain actions the adversary is allowed to take, and we want to prove that even though we have this other agent that can perform these actions, we still get the properties that we want from our system. So for example, in cryptography, the adversary might be able to obtain encryptions of messages of its choice, and it shouldn't be able to learn what a new ciphertext corresponds to, or any information about the message contained in a new ciphertext. In privacy, the adversary shouldn't be able to learn too much about individual data records. And in distributed algorithms, the property that we want is actually one of correctness or efficiency. The adversary shouldn't be able to disrupt the computation. Right. So now I'm going to switch gears and get back to sort of the problem I promised at the beginning of my talk, which falls into the domain of distributed algorithms. And it's a problem of population stability. Here's the idea. Suppose that we have a system of agents where each agent has very limited memory and ability to communicate with other agents, but agents have the ability to replicate themselves or to self-destruct. And suppose that we have an adversary that can delete or insert agents into the system at some bounded rate. So this may model, this can model a variety of ways in which things can go wrong. If we're thinking in a biological context, cell death, or if we're thinking about a noisy process, just any arbitrary behavior that's different from what we expect. It's sort of a very pessimistic assumption about how things can go wrong. And then in the presence of this adversary, we want to maintain the property that the total population size is roughly what it should be. It doesn't deviate too far from the target value n. So to specify the model a bit more, suppose there are initially n agents, and they have very, very low memory. Each agent only has log of log n bits of memory, roughly. And every round, agents interact by pairs of agents chosen at random are allowed to exchange messages. And then also each round, the adversary can insert some polynomial number of agents, a small polynomial number of agents. And the goal of the adversary is to make the population size at some point get sufficiently far from the target value, multiplicatively bounded away from n. So the goal of our protocol will be to make sure that this doesn't happen. This is kind of a very tricky problem. There are a lot of issues that come up when you try to solve it. The first and maybe most obvious one is that log n is really little memory. We're trying to make sure the number of agents stays approximately n, but each agent can only count up to something like log n or log squared n. So an agent can't view the entire state of the system. It only gets very local information based on interactions. But even if an agent could view the entire state of the system, it can't count that high. So a single agent can't really know whether the population is too large or too small. And also, agents don't have unique IDs. Every round, there's no consistent communication. Every round, you're exchanging messages with different agents. You have no way of identifying who you're talking to. So it's sort of very hard to aggregate information about what's going on. And then the adversary can make life even more difficult. So distributed computing is largely about coordination. So one of the basic techniques of distributed computing is something called leader election, where basically the agents agree on a single agent to direct everything that's going on in the computation to tell all the other agents what to do. But now that we have an adversary, leader election seems like a completely hopeless approach. Because suppose that one of the agents is elected as a leader, well, the adversary can delete it. And then you don't have a leader. Or the adversary can add 1 million agents that think they have a leader, and then everyone gets confused. So a lot of the standard approaches from distributed computing just don't work. So we're going to do something that looks pretty different. And the idea is that the agents are going to coordinate to sample from some distribution so that the approximate population size is encoded in the variance of this distribution. And then, based on very local interactions, agents can each obtain a very weak estimate of the variance and make individual decisions that globally will preserve the approximate population size. So we're going to start with this very basic fact about the binomial distribution, that if we flip a coin k times, and you look at what fraction of the coin flips came up heads, it's roughly 1/2 plus or minus 1 over root k, or 2 root k. So in particular, clearly, the more times you flip a coin, the more closely 50-50 it'll be heads and tails. So we're going to try to use this to figure out how we're going to have each of the agents flip coins, and we're going to try and use this to figure out how many agents there were and whether there are the right number, too many or too few. So here's the idea. Every agent flips a fair coin, and then you look at the color of, and uses that to choose a color, 0 or 1. And then each agent looks at the colors of the next 2 agents it encounters. And if those colors are equal, then each agent will replicate itself with some small probability. And if the 2 colors are unequal, then the agent will self-destruct. So the idea here is if the population size is too small, then you're more likely to have a much more skewed distribution of 0s and 1s. So you're much more likely to encounter agents of 2 different colors. You're more likely to encounter agents of the same color twice. Because, for instance, if there are many more 1s than 0s, you're more likely to encounter 2 1s than you would expect. Whereas if the population size is large, then there are almost the same number of 0s and 1s. And so you're about as likely to obtain 2 different colors as 2 of the same color. So this actually does give sort of the right behavior and expectation, but it's not good enough, because this is a random process. There's signal and there's noise. And with this version of the protocol, the noise is much larger than the signal. So actually, the population size will just behave like a random walk and will not be stable. So we need to do something to amplify this. And to do this, we're going to do a little more coordination in how we choose colors. So rather than having every agent flip its own coin, we're going to have only root n of the agents flip coins to choose colors. And then each of these will spread its color to an additional root n agents. And then we're going to run the same protocol to determine whether to replicate or to self-destruct. And I don't have time to go into the details of how to make this happen in low memory, but it can be done. And it turns out that this amplifies the signal enough that that the population size is preserved, and not only that, it's preserved even if the adversary can add or remove a bounded number of agents in every round. So this gives us a protocol that can maintain a stable population size with only log n bits of memory per agent, roughly, slightly more than log squared n different states per agent. 3-bit messages, which I didn't show you how to do, but this strategy can be implemented with very, very small message size, that can handle almost n to the 1/4 adversarial insertions or deletions per round. So this problem, I think, is only the beginning. And there's a lot of really interesting other questions that you can ask. For instance, we're talking about the population size, but we can also ask what other invariants of a system can we maintain in this type of adversarial environment or other types of adversarial environments. Also, this is a very sort of noisy model of communication where there's no consistency from round to round. Working in something like a network type communication model would be very interesting. And then also, we're not actually obtaining an approximate count of the population. We're somehow maintaining a stable population size without ever counting. But it would be interesting to see if we can use ideas from this protocol to obtain robust protocols for approximate counting as well. So I'd like to thank, of course, my advisor and my other co-authors on this project, Shafi, Raphael, and Alessandra. I'd also like to thank my practicum advisors, Aiden and Arifil at LBNL, where I worked on a parallel graph algorithms project. And then also CSGF and Krell and everyone who works to make this program happen. Thanks a lot.